Welcome back. Let us see the high frequency analysis of common emitter amplifier or common source amplifier circuits. In this case, I am taking this common emitter amplifier as an example in order to see the high frequency analysis. It includes, along with transistor and biasing circuit, a coupling capacitor, emitter bypass capacitor, a CL load capacitor. First of all, let me draw the AC equivalent circuit of this amplifier network using high frequency model. The two simplified high frequency model. The simplified high frequency model includes only two capacitances. One is C pi, this is the capacitance between base and emitter, and another one is C mu, this is the capacitance between collector and base. The rest of the circuit is, and here the assumption is, since with reference to higher frequencies, the coupling capacitor and bypass capacitors acts as short circuit. Therefore, the emitter resistor RE also acts as a short circuit. And assume the load capacitance in open. Assume here the load capacitance is in the open model. Therefore, the circuit is like this. Up to this is a transistor equivalent circuit. And in addition to this, at the output you have RC resistor and RL resistor comes in parallel, whereas at input R1 is parallel to RL called RB resistor, and Vs is as it is along with its internal resistance. Now, using Miller capacitance or Miller's theorem, the feedback capacitor or C mu is converted into Miller capacitance at the input side and shown in the another diagram here. Here RB is R1 parallel R2 and this R pi, C pi, Cm, and at the output side Gm, V pi, and the equivalent resistance of all these three resistors R0 parallel RC parallel RL is referred as RL dash. Okay. Now let us see first of all the Miller capacitance value. Miller capacitance value is given as the feedback capacitance is C mu into 1 plus AV. Okay, 1 plus AV. Here the AV is the output voltage, that is Gm V pi, okay, minus Gm V pi into RL dash divided by what is the input voltage V pi, okay, V pi, that is at the base. The base is V pi, okay. So therefore the AV is Gm RL dash, okay, where RL dash is, it is a parallel connection of small r naught, RC and RL, okay. And using the time constant technique, you can write out the corner frequency or upper 3 dB frequency or higher cutoff frequency as fh equal to 1 by 2 pi tau p, okay, 1 by 2 pi tau p, okay. This is the with the time constant technique. You can express the corner frequency like this, where what is tau p? Tau p is the product of equivalent resistance and equivalent capacitance. Tau p is the product of equivalent resistance and equivalent capacitance. At the input circuit, if you see, the equivalent capacitance is Cm plus C pi, since these two are connected in shunt, and equivalent resistance is R pi parallel RB parallel RS, okay. Now, including these two in the corner frequency, it becomes like fh equal to 1 by 2 pi of R pi parallel RB parallel RS into C pi plus Cm, okay. So this is the higher cutoff frequency. So if you see the midband voltage gain of this circuit, okay, the midband voltage gain, that is the gain from V0 to Vi, which is given as Gm RL dash into Vi means the resistive part is included, that is including the RS. It includes the RS value as Rp parallel Rpi divided by Rp parallel Rpi plus RS, because the V in terms of V pi in terms of Vi is like this. Okay, so therefore this is the midband gain and this is the corner frequency. So therefore the Bott plot you can draw with reference to this amplifier is like this. Okay, this is the midband gain and FH represents the corner frequency, right? Similarly, in the next class you can see the high frequency analysis of common base amplifier, common gate amplifier and cascading circuits. Common base is in the transistor version, common gate is in the FET or MOSFET version, and cascade circuits. Okay, in cascade circuit what happens that we have to see. Okay, thank you.